Hello, thanks for dropping by my presentations. Um, this presentation needs go along with the poster that you see. I encourage you to check it out for the key um, results and the big picture of the whole study. So in this study, I want to tell you my exciting results on using computer simulations to help design materials not just look like biological systems, but also being able to perform functions like them from self and directed assembly, so-called bottom-up approaches. First of all, I want to thank my excellent collaborators over the years that are very helpful and inspiring to this work, as well as the funding agencies assisted in here. The motivation of the work comes from the fact that such kind of materials have offered us a lot of promising solutions to address global issues in healthcare, environment, and energy. I'm showing you here three examples of using those materials in biointegrated electronics, bioremediations, and structural batteries to tell you that we can explore lots of things down to the nanoscale by making materials interact, uh, compatible, and function like biological uh, structures. What is interesting here is that we have been seeing an emerging paradigm for engineering biomimetic materials from bottom up. The idea here is to use hundreds of millions of building blocks coming from the biological world and the synthetic ones so that we can bring the functionalities and biocompatibilities combined with the strength and sensings and actuating capabilities of the synthetic building blocks. It all boils down to our ability to being able to understand and to control over the interactions between those building blocks. Of course, the challenges here are enormous, even though they seem very straightforward. What are the desirable morphologies that we need to start from? How do those building blocks interact? How to direct them into the structure that we want? And how to make those structures behave like biological matter in the sense that they need to be responsive to environment change in a controlled manner like temperatures, pH, or light. That's where my research fit in. Over the years, I have been using computer simulation to help experimentalists design and to predict uh, the different structures coming from polymers, colloids, quantum dots, which have been using a lot of in application areas as is shown here. What made my research stand out from many entering the field so far has been the fact that I actively involved in the development of new tools, advanced computational tools. In this case, using uh, graphics processing units. In this slide, I show you the performance boost for different kind of systems that I have been helping to make them much faster. The speed up can range from 5 times to 20 times compared to the runs without the GPUs, even with the very modern CPUs nodes these days. And with that, I have been awarded by as a members of the LAMPS development teams 2 years ago. Not only making the simulations much more efficient, I also help the developing new algorithms to make the system to make the simulations sample and simulate the big system, uh, giving more reliable outcomes. When you have millions or thousands of particles come together and form some structures, it's very likely than not that those structures are not representative of what's going on in realities because of the fact that the system can easily track in those uh, uh, metas, metastable states as shown in the red dots here. So that's where those algorithms are about. It helps us to make the system escape from those traps or bridge the different time and length scales by coupling with the continuum uh, approaches or improving the statistics of the results by different kind of scheme to sample the phase space better. So with those advanced tools in the performance of the code, in the algorithm to sample the system better, I have been able to help experimentalists explore a lot of uh, submarine systems. In this case, I'm looking at how proteins and particles and protein and polymer interact and to assemble into various biomimetic nanostructures. I will leave the protein polymer systems for our discussions and only focusing on one of the very exciting results on the mixtures of polymer nanoparticles and proteins in this presentation. This initiated by Nick Kotov and his group, where they want to control the size of the clusters forming by nanoparticles and proteins. Both have same charge, a similar charge around 3e. When those two building blocks come together, they form clusters of 100 nanometers in size, as shown in the size distribution on the right. And the size, those clusters are much bigger than the individual building blocks. You can see the particles at around 5 nanometers. And these clusters remind us of the virus capsid. So why they form? What is even more interesting for this case is that those clusters remain separated even when they are jammed together. As you can see in the one on the right, those building blocks, those clusters remain separated and they form a kind of what they call uh, crystals making from the colloidal particles. So simulations come in trying to understand what's going on and what determines the final size of those clusters. The well-celebrated description of these systems in the field has been the DLVO. As you can see, this model uh, represents the interaction between the particles of charge Qi and Qj in the solvent of dielectric constant epsilon r can be described by three terms as shown in here. And the assumption here is that for a given ionic strength Qi and Qj and epsilon r, the repulsion between any pairs of particles is a function of the charge Qi and Qj and epsilon r. The Aij is fixed for a single simulation run. However, this model can only conform to the classical nucleation theory, which states that beyond the critical size of the cluster marked by the triangle here, we cannot see any finite size or uniform size clusters as in Nick-Kotorp systems. Otherwise, instead, they form infinite size cluster. All the particles come together and form very huge cluster. So what I did in this study is to go back to where it started. You can see when the particles come together and start forming clusters. What we are seeing here is the emergence of an interface between the cluster and the solvent, and in the electric constants inside those clusters, because of the more and more charge inside those clusters, the electric constants inside keep decreasing up to the point that the electric mismatch causing the surface polarizations that repel all particle approaching the cluster to be repelled away. That's why the cluster acquire their final size. So what I did is to modulate the strength between the two particles having the charge I and J, separating them into two kind of interactions inside the cluster by A intra and from different clusters A inter. And A inter vary linearly with the side of those clusters at the first order expansions. And here the parameter S characterize how strong particle inside cluster are repulsive to anyone from outside. And this model have been able to capture the behaviors we observe in experiment by looking at the cluster size histogram over time with the initial broad distribution until we see a very sharp peak at the final size, similar to what we see in experiment. And the cluster do stop when they acquire the final size, even they are very densely packed. And with this model, we've been able to predict how to control the size of those clusters. In this case, we can increase the ionic strength. From that, we can decrease effective Coulombic repulsion strength between two particles, and we can lower the, the final size of those clusters. Those predictions have been confirmed by Nikotov and his group. So to summarize the benefits or the advantage of using computer solutions here is to that we can, it's not only we bring into the table insights into the nanoscale interaction between the proteins and the nanoparticles, but also we can predict what's going on if you want to control the size of those clusters. And our model is a significant improvement upon the classical nucleation theory by capturing the final size of those like charge clusters. And this also bring this system to be similar to other biological matter, for example, viral capsids or microtubules or geometrically frustrated assemblies. And to summarize, the theme of this work is that we can uh, combine modeling, simulation, and data into giving the physical insights into nanobiosystems, and also give the design rules that can be tested in experiment towards designing biomimetic materials from bottom up. And the whole picture is to find, explore, and to accelerate the process of finding new materials that address the global issues in healthcare, environment, and energy. And the cluster I'm showing you, and the cluster, the random copolymers and protein systems are used in bioremediations and bio catalysis uh, already. So I want to stop here and encourage you to check out my poster, and we can discuss, and uh, I will answer. I'm very happy to answer your questions you may have. Thanks again for dropping by, and I'm here. Thank you.